Okay, great. So we've hit the hour. So I'm going to get started for everybody that's watching today. And yeah, you should see that on YouTube we have a live chat where we have a couple people, Chris Rakakis and Simon Byrne, who will be answering questions. And also, you'll be able to interact with all the tutorial materials that I'll be using on juliabox.com. So if you want to log in there, you can use your GitHub credentials, Google, or LinkedIn. And that's where we host remotely some Jupyter notebooks that will allow you to play around with Julia and get comfortable in this environment without installing anything. So let's get started. First off, my name is Jane. I work for Julia Computing. I just started there a few months ago, and about once a month now we've been doing these introductory tutorials on the Julia language with the hope that this will make the language more accessible, just give you more resources for getting up and running with it. In addition to the tutorials that I've been doing, you'll be able to see a schedule that includes other tutorials about the Julia ecosystem on julialang.org/learning. So there you can see right now we have this tutorial happening now. Tomorrow we have the same tutorial but taking place in Spanish that Miguel Raz Guzman will be hosting. And then we have a couple other package tutorials coming up in May. So on May 10th, George Datsaris is going to give us an introduction to dynamical systems in Julia. And though you can't see it on this image, on May 24th we'll also be having an introduction to data frames happening. At the end of the tutorial, so once you're on JuliaBox and are able to see all of the notebooks that we'll be working in, the last notebook we'll be working in is notebook 12, and you'll see that at the end of that notebook there is a link. It's tinyurl.com/intro julia feedback. And if you wouldn't mind taking just like a second to fill that out at the end of the tutorial, that would be super helpful. It's 4 questions, and the point of that survey is to give me a sense of, I guess, whether or not these materials are well targeted to entry-level users to Julia. And so yeah, that would be very helpful to know how this tutorial made you feel about learning the language and how well it addressed your interest in learning the language. So before we dive right into the tutorial, I wanted to give you a bit of a sense of why we might be interested in learning Julia and what makes Julia special. So before the tutorial itself, we're going to talk about the question, why do we want another language? And then we'll see an example of using Julia in practice. So this first question, why do we want another language? So I found this image online from Craft to Coding. It's basically a periodic table of computer programming languages rather than of elements. So just, by taking a glance at this, we can see that there are tons of different languages out there. And so then the natural question to ask is, well, if all of these questions exist, they each are bringing something different to the table, presumably, like why are all of our needs not already met? Why would we want an additional language on top of all those that are already existing? And the answer is that in spite of, all of the languages that are out there, we still have a problem, which is called the two-language problem. So what is this two-language problem, you might ask? To explain the two-language problem, you have to go back first to the sort of classical observation that languages tend to fall into one of two camps. On the one hand, we have these lower-level languages that are more performant, so languages like Fortran or C. And on the other hand, we tend to have these higher-level languages that aren't as performant. They don't run as efficiently or generate as efficient machine code, but they are more productive for us as programmers to work in because it's a little bit easier for us to express our ideas in our native language in these computer languages. So for example, Python, Ruby, and MATLAB would fall into this sort of like productive language category. So we have sort of this dichotomy between performance and productivity, but really we need to talk about a third variable too, which is generality. So the reality is that if you really just wanted to write fast code easily, there are domain-specific languages or special libraries that might allow you to do that. So for example, if you're working in Python, if you really need speed, you might move to NumPy, for example. NumPy is going to allow you to work really quickly with arrays. But then the scope of that, special library, and similarly with, domain-specific language, the scope of those will be limited. So if you really want to be able to write general-purpose software and simultaneously get performance and productivity out of, the language that you're using, you end up with this trade-off, and you're kind of, between a rock and a hard place. And so the classical workaround to dealing with this issue is to use 2 different languages. So this is where the name the two-language problem comes from. So typically people will prototype in one language. They'll prototype in a language like Python. And then once they have something running, after they've sort of done like a proof of concept and they have something working, then they'll translate that code into a lower level language like C or Fortran to be able to get, hit production scale. And so the idea is that Julia is designed to address this two-language problem. And the tagline that we have for Julia is, looks like Python, feels like Lisp, and runs like C or Fortran. And so let's break this down to see what we mean by this. The idea is that Julia offers productivity, generality, and performance. So let's start by talking about performance. Now in Notebook, I just reordered the notebook, so I think it's now Notebook 10. No, it's Notebook 9. So Notebook 9, we're going to see this notebook called Julia is Fast. And in that notebook, we're going to do some benchmarking of different implementations of the sum function. So this sum function is going to take a vector and then just add together all the different elements of that vector. And what we're going to see is that when we do this operation in C, and I should note first, when we're talking about, on this slide, when I'm talking about comparing implementations of sum in C, Python, and Julia, I'm talking about comparing handwritten implementations. So the same algorithm is going to be used to compute the sum in all 3 cases, where we're just going to loop over all the elements of this array. and see how long it takes to add together the elements. And for benchmarking purposes, we're going to use a 10 million element vector. And so this is going to take order of 10 milliseconds when we do this operation in C with our handwritten implementation of sum. Then when we move to Python, it's going to take order of 500 milliseconds. And when we go to Julia, we're going to be back down to approaching C speeds at order of 10 milliseconds. So this gives us a sense of Julia's performance, Julia's ability to execute code quickly. And the next thing that Julia has to offer is productivity. So if we were to look at the code for those handwritten implementations of sum side by side in Python and in Julia, what we see is that they're really not very different. So there are a couple differences in keywords. On the left, you'll see that in Python, for example, we have the def keyword and a couple of required colons. On the other hand, in Julia, we have the function and the end keywords. But other than that, we can express ourselves exactly the same, with the difference that in Julia we're getting more than a factor of 10 increase in performance. And the third variable then that we were going to talk about is generality. So working in Julia really feels like working in a Lisp, in that it offers metaprogramming facilities. For example, the design paradigm, which we're going to talk about later in this tutorial, is multiple dispatch. Julia offers macros, and the fact that Julia is really such a general, expressive and powerful language allows Julia to mostly be written in Julia itself. And one of the things that's really cool about the fact that Julia is mostly written in Julia is that this really starts to blur the line between users and developers of the language. So a lot of our most important contributors to the language are not, they're not computer scientists. They're people in various areas of STEM or economics, for example, that have come to the language as users and found that they were able to basically look under the hood and see what was going on in the source code, because as a user they knew Julia, and then they could look inside and see more Julia code rather than needing to jump to a lower level language in order to understand what was going on in the code that they were using. And then they were able to make contributions to the language. So this is really cool, and hopefully, if you're inspired enough by this tutorial to keep learning the language and jump in, then hopefully we'll see some more contributors coming on board. Okay, so now that we've talked about why Julia is special, let's talk about what this actually means in practice. So one really great example of Julia being used to do cool things is the Celeste project. So the Celeste project took data from the Sloan Digital Sky Survey, and that was an effort to collect data on about 35% of the visible sky. And so in collecting all of this data, about 178 terabytes of data were generated. So that's 1.78 times 10 to the 14 bytes. And to give you a sense of scale, I've given a couple comparisons here, where if you were to try to store that much data on DVDs, it would take over 25,000 DVDs to store that amount of data. And similarly, if you wanted to do something absolutely ridiculous and try to print all of that on paper, you would need like over 150,000 pickup trucks to store the amount of paper that you might generate from that. Okay, so the people that were trying to initially trudge through this huge data set didn't have an easy time with it. And then what happened was that a team of researchers came together to form the Celeste project. So this involved people we had someone from Julia Computing, people from Lawrence Berkeley National Lab, MIT. I'm trying to remember, I don't feel super confident about about what other institutions were involved, but there was a big team of researchers that came together. They decided to write software exclusively in Julia that would run on NERSC supercomputers up at Lawrence Berkeley National Lab in the Bay Area. And so what they were able to do, harnessing both the power of Julia and then supercomputing machines as their hardware, was that they were able to catalog 188 million stars and galaxies. So this meant identifying the locations, the brightnesses, the morphologies, and the colors of all of these different astronomical objects, and they were able to do this entire calculation in under 15 minutes. Now in doing the calculation, Julia became the third language to join the Petaflop Club, so Julia hit over 1.54 petaflops per second. And doing this calculation also took over 1 million threads and 9,000 nodes. So this gives us a sense of Julia's ability to really run parallel code on next generation machines. So the next question is, why was Julia the language that they chose to work in for this Celeste research project? Oh, and I just saw, yeah, so later on, I'm going to add the feedback link that I showed earlier to the description of the YouTube channel, or yeah, the description of this YouTube video, so that it will be easy for everybody to find. But for now, so the next question is, like, why did the Celeste research team work in Julia, and what did Julia bring to the table? So the first answer that you might come up with, given that we know that Julia is designed to solve the two-language problem, is that maybe the people working on the Celeste research team saved some time because they didn't need to basically write their software twice. They didn't need to prototype in one language and then translate to a lower level language. And while that's true, really the impact of using Julia in this project was more profound than that, because the way that a large project like this would have typically gone is that you would have had different people doing that prototyping in a higher level language and writing the lower level, performant code. So typically a team like this that brings together people of various backgrounds, like statisticians and domain scientists, as well as computer scientists, typically the way this would work is that the domain scientists would be the ones to write that higher level code. And then when they're done, they would probably pass the baton off to the team of experts that would have really focused on the high performance computing aspects of the project. So instead, the fact that everybody was working in Julia, that everyone was working in the same code base from the beginning, meant that the team was really able to function as a team. They could really work together, they could iterate more rapidly, and in the end this meant that the implementation of the science and the science itself were able to really evolve as one. So this is an example of Julia in practice, what Julia can do. We're approaching our 1.0 release. Right now we're seeing about 150,000 downloads per month. And as of January 2018, we had over 1.8 million downloads. Now that we're approaching 1.0, it seems like we're starting to hit exponential growth, so our community is growing and we hope that you'll become a part of it. Also, one last thing before we dive into the tutorial, which is that after this tutorial, there are lots of other resources out there for you to get up and running with the language. And so we have active communities on Slack, Discourse, and GitHub. So if you're interested in joining any of those communities, there are lots of friendly people to answer your questions, help you onboard if you're interested in contributing to the language. And beyond that, if you want to reach out to me, my email is jane@juliacomputing.com, and I'm happy to try to be helpful and redirect you if I'm unable to answer any of your questions. And with that, we can dive into the tutorial. So let's see, I'll go back here and all right, so once you log into JuliaBox, this is the screen you'll see. So again, this is juliabox.com, and once you're here, you can go to the tutorials directory, then intro to Julia, and then that's where you'll see the notebooks we'll be using today, which start with 00 and then go to number 12. And I'm going to grab that link with feedback from number 12 first and see if I can quickly pop it into our YouTube description so that you'll be able to see it more easily. Whoops. Okay. So I'm gonna pop here so you remember. Okay, so just take a moment to get to tutorials, intro to Julia, and then open up this first notebook as 00, and I'm going to add this link. Oh, somebody just said repeat my mail ID. That is jane@juliacomputing.com. And I'm also, well, on GitHub I'm xorjane, and on Twitter I am, well, and off Twitter I am Jane Harriman. So you should be able to find me with that information. Okay, I believe I have updated the YouTube description such that the feedback link should be there. Let me check to make sure this worked. Yes, okay, all right. Our feedback link is now in the description underneath the YouTube channel where you're watching. Okay, cool. Well, with that, I will return to our Julia Box notebooks. Okay, I'll leave that. All right, so starting with notebook 00. So the purpose of this notebook is to get you comfortable, or just to show you how to function in a Jupyter notebook in case you're not familiar with that. So the first thing you need to know is how to execute code. So in a Jupyter notebook like this, we have these markdown cells where some of the instructions and explanations are provided in regular text. And then we write code in these cell blocks that are preceded by these input names. And so if we want to execute a cell, we can hit Shift and return. Alternatively, we could go to cell from this drop-down menu and hit, for example, run all or run cells. Also, we can use this run button here, the one that looks like an arrow facing a wall. And one of the things you'll notice is that here a 4 was printed to standard out. So by default in a Jupyter notebook, the last line of any code block is going to print a standard out. And if you want to suppress that output, you can put a semicolon after the end of the last line. And if you want to print other lines that are higher up, for example, you can use the println command, and we'll see that in the next notebook too. Whether you are in a Jupyter notebook like this, or if you're at the REPL, for example, you can get documentation by preceding any function that you're not familiar with a question mark. So here I say question mark println, and then I get all the docs that exist for println. Similarly, if you want to get into shell mode, you can just precede any shell command with a semicolon. So here if I do semicolon ls, I can see all the files in my working directory, and if I say semicolon pwd, then I can see what directory I'm in right now. So that's how we can navigate, find our way around inside a Jupyter notebook, and with that we can move to notebook 1. Which is getting started. Okay, so in this notebook we're going to see how to print, how to assign variables, how to comment, and just take a look at what the syntax for basic math in Julia is. So first off, we often print in Julia with this println function. So here I've just thrown a string inside there. If we want to assign variables in Julia, all we need is the variable name and the value and an equal sign. We don't need to worry about types. Julia will figure out those types for us. So for example, here I'm creating 3 variables. One is called my answer, and Julia recognizes that that's an int 64. When I create the variable my pi, Julia sees that that's a float 64, and here I'm using the smiley cat emoji to store the string smiley cat. And so another thing is that after we've assigned a value to a variable, there's no issue with reassigning that variable to a value of a different type. So smiley cat used to be a string, but now if we look at the type of smiley cat, it is an integer. And this is a good time to note that Julia allows us to write super generic code, and programming in emojis is a great example of that. So for example, we already have smiley cat equaling 1, so I can put these other emojis equal to other values, and now I can do things like this, where we can see that smiley cat plus frowny face equals happy face, and that is a true statement, always, unless you have a cat allergy. So, commenting in Julia. To comment, if you want to have just a single line comment, you can precede that comment with a £, hashtag. And then if you want a multi-line comment, you can enclose your multi-line comment inside a pair of hashtags and a pair of equal signs. And then, syntax for basic math will probably look pretty familiar to everybody, unless, I think the one thing that's probably a notable difference is if you're coming from Python, we're using the caret sign here to exponentiate as opposed to the double star. And also, maybe one operator that's a little bit less familiar is the percent sign that we can use to get the modulo, or the remainder. So, I don't think I'm going to go through the exercises today, but note that inside, let's see, where is it? We have exercise solutions. So if during the tutorial or thereafter you want to try to play around with some of these exercises, you can always check how you're doing in the exercise solutions thereafter. So with that, we're done with notebook 1. And we can move on to notebook 2 on strings. Okay, so in this notebook, we're going to see how to get a string and then how to interpolate and concatenate them. So first off, how to get a string. So to get a string, or to create a string, we can enclose some characters in either a single set of double quotation marks or a triple set of double quotation marks, with there being a couple differences between these two ways. So for one thing, if we try to quote something with double quotation marks inside this first type of string, we're going to get an error. And the reason is that it's sort of ambiguous where our string actually ends. So for example, is that the full string, or what have you? But it's unambiguous where the string ends if we try to use double quotation marks inside a string that is created from enclosing text inside 3 double quotation marks. So for example, we can do this without getting any errors. And beyond that, you can also do some additional formatting more easily inside strings that are created with this triple set. Another thing to note is how not to define a string, which is with a pair of single quotation marks. So you can see here, if I look at the type of A here, A is a character rather than a string. And if I try to enclose multiple characters inside a set of single quotation marks like this, we're going to get an error. Okay, so next, interpolating strings. So say that I want to have a variable or an expression even evaluated inside a string that otherwise just contains text. So we start by here just initializing these 3 variables, so name, and then the number of fingers and the number of toes that I have. And now if we want to throw these values inside a string, we can just put a $sign next to the names of the variables that we want to be used as placeholders, for the actual variable. So if I say, hello, my name is $name, I'm going to end up getting, hello, my name is Jane. And then here, similarly, I'm throwing the numbers 10 and the numbers 10 inside this string. And then if you want to evaluate an expression inside a string, you can use the same $sign, but now enclose the expression you want to evaluate inside parentheses next to that $sign. So if we do this, now we've added 10 and 10 together to get 20, thrown 20 in the string. Okay, so there are 3 different ways that I'll show to concatenate strings together. So we're going to start by creating a few new variables. So we have S3 and S4 are 2 strings, and then we have the smiley cat emoji returning to us, and smiley cat is equal to 10. Okay, so the first way to concatenate strings is to use this string function. So here we're adding, or we're passing to string the variables S3 and S4, and we're getting this single output string. How many cats is too many cats. And string takes arbitrary numbers of arguments. So here I've given it just 2 input arguments, but if I wanted to pass it, 3 or more, for example, I can do so. And also string will take non-strings as inputs and return them as strings. So for example, now I am going to create this response. The string, I don't know, but 10 is too few, and I've done that with 3 input arguments, one of which was passed as an int64. The second way that we can do string interpolation is to make it look like we're multiplying 2 strings together. So here it looks like S3 times S4. And the third is that we can rely on string interpolation. Sorry. Okay, I think I said something incorrectly before. I think I mixed up the words interpolation and concatenation, or maybe I just forgot myself. But S3 times S4, or what looks like that, is concatenating strings. And then here I'm using string interpolation to concatenate by putting $signs next to S3 and S4. And one thing I am going to note, otherwise not doing these exercises, one thing I'm going to note is that if you use exponentiation in Julia, under the hood you're calling the multiplication operator. And so if I write something like this where it looks like I'm exponentiating a string, I'm really going to get concatenation of the high string 1,000 times to get one really long string. That's worth pointing out because it's cool. Okay, if you have any questions, just feel free to ask on chat. Okay, so our next notebook now is on data structures. Okay, so the three data structures that we're going to talk about are tuples, dictionaries, and arrays. So the first data structure, a tuple, for those of you that aren't familiar, we can create by enclosing an ordered collection of elements. So tuples are immutable, so once we've created them, we cannot update them, and they are ordered. Arrays, we'll see later, are also ordered, so we can index into them and grab numbers at particular locations, or grab values stored within the tuple at particular locations within the tuple or within an array. Okay, so tuples are ordered collections of elements that we store inside parentheses in Julia. So this is the general syntax, and then my example of creating a tuple here is this one called My Favorite Animals. Because they're ordered, we can index into them. So here I'm grabbing penguins. And note that Julia is one index, so we start counting from 1 rather than from 0. And so that's why we're grabbing penguins here when we say My Favorite Animals 1 rather than grabbing cats. And then, because tuples can't be updated, penguins will forever be our first favorite animal. And we can't add otters now to this tuple. Now the next data structure of interest is the dictionary, where we're going to create associative relationships between key and value pairs. And the syntax for creating a dictionary is to use this dict keyword. And inside the parentheses that follow that keyword, we're going to have keys to the left of arrows that we create from equal signs and then right pointing arrowheads, and then values to the right of those arrows. And so my first example and one thing I am going to say is that if we wanted to, we don't need to add key value pairs at the time that we create a dictionary. So for example, I could just call the dict keyword and create this empty dictionary. Or I can create a dictionary that has entries. And so here I'm creating a dictionary called My Phone Book, where the keys are names and the values are numbers. And so we can see that if we want to perform a lookup now, if we want to grab a value associated with a particular key, we can throw the key of interest inside square brackets after the name of our dictionary. So here, we get Jenny's number. Similarly, if we want to add entries to an existing dictionary, we can use My Phone Book, or rather, we can use the name of the dictionary, square brackets, and then throw the key from the key value pair that we wish to add to that dictionary inside the square brackets after the dictionary name. So here I've done that, and then the value associated with the key Kramer is Kramer's phone number. So when we do that, we've just added Kramer to My Phone Book, and we can check that by looking inside My Phone Book and seeing we now have 3 entries. Another way to edit or mutate a dictionary is to use this pop bang command. So that will allow us to delete key value pairs from dictionaries. So pop bang by default, pop bang is going to take the name of the dictionary you wish to mutate as the first input argument, and then the key from the key value pair that you're trying to remove as the second input argument. So when we do this, we're going to remove Kramer from the phone book. Note that we've also, in calling pop bang, we have returned the value associated with the key that we just removed. And also, when I say pop bang, what I mean is the function called pop that is followed by an exclamation point. And we'll talk in a later notebook about why there's an exclamation point there and what it signifies. But now we can check to see that Kramer is removed by calling My Phone Book again. And there we only have Jenny and Ghostbusters. And then dictionaries are not ordered. And so that means that if I try to get like the first input or the first key value pair in My Phone Book, that doesn't make sense because there is no first key value pair. Instead, Julia thinks that we are looking for some value, some key that is the number 1. And here key 1 was not found because there was no key value pair with a key of 1 added to this dictionary. One other thing I want to say before we move on to arrays is that you can get information about the types that Julia has inferred exist in a data structure like a dictionary by looking at this line that shows up when you initialize a dictionary. So in this first case, when I initialize an empty dictionary, Julia can't guess at what the entries to this dictionary are going to be because there's no additional information passed other than that we just want a dictionary that we're going to presumably add information to later. And so Julia has declared this dictionary such that it will contain keys and values each of the any type. And maybe this is beyond what you'll need to know today if you're just getting started with the language, but for those of you that are interested and maybe want to look this up later, we have a type hierarchy in Julia that is based on both, or that uses both concrete and abstract types. So we have these concrete types like int64 and float64, and then we have abstract types like number and any, for example. And this any type means any possible concrete type. The number abstract type, for example, includes all integers, all floating point numbers, but not strings, for example. But that's kind of beyond the intro tutorial. But in case you are interested in that, I wanted to point that out. And similarly, if we look at my phone book, here we did pass entries when we initialized the phone book, and so Julia is able to infer, like, okay, this phone book looks like it takes keys that are strings, similarly values that are strings. And that means that if we tried later to add key value pairs to a dictionary that already has like a set type, and if we tried to add key value pairs that were not for example strings and strings in this case, we would get an error. So that's worth noting. But in the exercises, if you go through those later, you can see that there are workarounds for this by adding type information at the time you declare the dictionary. Okay, so our third data structure, and the one we'll spend the most time on here, is the array. And so, like tuples, arrays are ordered collections, but now we're enclosing those ordered collections inside square brackets. In addition to being ordered, another notable thing to say about arrays is that they are mutable, so we can update them after we've created them. So with that, create our first array, my friends. And here we can see, for example, that this is an array that contains strings. What this is saying here, this bit, is saying that this is an array that is one-dimensional, and the one-dimensional array contains strings. Similarly, if we were to look at Fibonacci, here we're saying this is an array that is one-dimensional, and that one-dimensional array contains N64s. Now, if we want to have an array that has a mixture of different types, we can create one like this. And in this case, we see that our 1D array is storing elements of type any, just like the empty dictionary that we initialized above. And now that we have these arrays, we can index into them. So for example, the third element in my friends was Barney, and so we did that by just throwing square brackets after the name of the array, and then putting the number of the index we're interested in, the index we're interested in square brackets. And if we want to update existing elements of an array, we can do that by using this same indexing scheme, and then on the right side of an equal sign, we put the new element that we want to store at that point in the array. So with this command, I'll be replacing Barney with Baby Bop. And maybe just to check, to convince you that that worked. Okay, so there we go. Barney has been replaced. Two other commands that we can use to update arrays are the pushbang and the popbang commands. And so pushbang is going to always add new elements to the end of an existing array. So we give as the first input the array that we want to update, and as the second input the value or data structure that we want to add to the end of the array that we are updating. So when I call pushbang on Fibonacci 21, remember that Fibonacci before ended with the number 13. So now that I've pushed 21 onto it, it now ends with 21. Now, if I wanted to remove whatever's at the end of the array, then I could call popbang Fibonacci, and if we run that, we see we're back down to 13 being the last number, and if we were to run this again, then we would pop off the 13. Okay, here we go, and now we run Fibonacci. Now 13 is gone, and we're back down to 8 as our largest number. Okay, so these examples of arrays, my friends, Fibonacci and then mixture, those are all 1D arrays that only contain scalar values. But if we want to, we can create arrays that store, other data structures, other arrays, for example, as their inputs, or we can create multidimensional arrays. So let's start with an example of arrays of arrays. So this first one, the first element now of this array favorites is going to be this array of strings that says Cude, chocolate, and eggs. And if we look at this signature, what this is telling us is we still have a one-dimensional array, 1D array, but now the inputs in that 1D array are other 1D arrays that contain strings. Similarly, if we were to look at this numbers array of arrays now, we can see that this is again a 1D array, the one here and the array there, and now it contains as elements arrays of int64s. Now one command that allows us to generate multidimensional arrays is this rand function. So rand takes arbitrary numbers of arguments, and those arguments will specify the dimensions of the array that we wish to create. So here I'm creating a 4x3 2D array. Here I'm creating a 4x3x2 3D array. And in both of these cases, all of the elements of the created arrays are just going to store random values between 0 and 1. Though we'll see in a future notebook that if you want to randomly populate from some other collection or sequence, you can do that. But that's, later notebook. Okay. So one last note about arrays before we move on to notebook 4 is that we want to be careful when we try to copy arrays. So for example, we already have this array called Fibonacci that goes from 1 to 8. And let's say that we wanted to copy Fibonacci into some array called sum numbers. Okay, so now I have an array called sum numbers. If I wanted to, for example, update sum numbers, specifically here I'll update the first element of sum numbers, which is currently 1 to 404. And maybe we'll look at some numbers to see that happened. Okay, cool. So the first element of sum numbers is 404. When we look at Fibonacci, we see that Fibonacci's first element is also 404. And the reason is that when we made this assignment, we said sum numbers equals Fibonacci, we weren't actually creating a new array. The array sum numbers and the array Fibonacci at this point are the same array. So they're just two different names for the same object. And it doesn't matter if we call that array by its first name or its second name, whether we call it Fibonacci or whether we call it sum numbers when we perform an update. In either case, we're updating the same array, and then we'll see the result of that, again, using either name. Okay, so let's restore Fibonacci to its original state. Okay, so now Fibonacci starts with 1 again. So if you want to actually copy an array so you don't run into issues like this, you're going to want to use the copy function. So the copy function here, and this is a shallow copy. If you want to get a deep copy, you would need to use the deep copy function. But yeah, so if you wanted to copy an array, we would use the copy function. So here I'm actually copying Fibonacci, creating a distinct array called sum more numbers that has the same entries. Now if I update, I'm going to update sum more numbers, and I'm also going to look at sum more numbers. Okay, cool. So now we've updated sum more numbers, and we see that the first element of sum more numbers is 404. Now if we look at Fibonacci itself, Fibonacci still starts with 1, so we didn't update Fibonacci, which is good. All right, so that's notebook 3. Leave there, and our 4th notebook is on loops. Okay, so we are going to see in this notebook the syntax for while and for loops in Julia. So we can start with a while loop here, where the syntax is to use the while and the end keywords, and then we typically have some condition on the first line after the while keyword, and then we will have our loop body sandwiched between the lines that have these while and end keywords. So for example, we could count to 10 with a while loop this way, and we could iterate over an array and greet all the elements of an array with this way with a while loop. Note that Julia, for the most part, is not white space sensitive, so if I wanted to add like arbitrary numbers of spaces, that works the same way that it did before. And the reason for that, in case you're interested, or one way to think about it is that we have this end keyword, so that tells us where the loop ends, such that we don't rely on white space or on any particular set of indentation to tell us about the structure of our code, though it's still nice or visually pleasing to indent consistently. And okay, so syntax for for loops. So to write a for loop in Julia, you can use the for and the end keywords. We also have this in keyword, which we use to denote that we want to take our local variable that we're creating in that for loop over all the different values of whatever our loop iterable is. So this loop iterable is going to be probably like some array or a range or something like that. And then for each iteration of the for loop, we'll enter the loop body. So for example, here we're counting from 1 to 10 with a for loop. And here we are iterating over that same array with a for loop. Okay, so now let's use some for loops to create addition tables, which will show us a couple different ways to embed for loops in Julia. So we can start by creating a matrix of zeros, here called A. And so we're doing that with this fill command. So note that fill here, I'm passing 2 input arguments. The first is this 0, and that first argument is telling us what I want to fill all the entries in the subsequent array that I'm creating with. And then the second input argument is a tuple, and that tuple can have as many entries as I want, where those entries will specify the dimensions of the array that I'm creating with the fill command. So here, m and n are 5 and 5, and so here I'm creating a 5 by 5 matrix of zeros. And now I'm going to use this embedded for loop to loop over all the entries of this matrix and then update them so that every entry is equal to the sum of the row and the column index. So we've done that here. But if we wanted to do this, with only one for keyword and only one end keyword, we could with some syntactic sugar in Julia. And so let's do this exercise again, where now we're using the fill command to create a matrix called B. And now we'll iterate over B and create the same addition table, but this time what we've done is we brought that second line from our last for loop, the second line that started with a for keyword, and we've brought it onto the same line, or the same first line that we had before. So previously, I'm going to scroll up, we had the second for here, j in 1 to n. Here we've brought j in 1 to n onto that first line, and we have just a comma to separate I in 1 to m and j in 1 to n. Also note that we now only have one end keyword. And then maybe the third way that we might create an addition table like this is with an array comprehension. And really what I should do here, I haven't shown array comprehensions yet, and I know that for some of you watching that will be unfamiliar. So if you wanted to do just like a one-dimensional array comprehension, right here, it doesn't really matter what it's called. So in an array comprehension, we create an array from square brackets as before, but now inside those square brackets, instead of explicitly writing out all of the elements or what have you that we want to store inside that array, we can put code that will generate the array that we want. And so, for example, if I wanted an array that contained numbers between 1 and 10, I could say x is going to be the entry that I want you to add to this array. For x in 1 to 10, where now 1 to 10 is a range, or 1:10 is a range in Julia. So if I run this, I am creating just a 1D array here that has the numbers 1 to 10. And if I wanted to create a multi-dimensional array in this way, I could just add, other, for example. So that's a rather large addition table and the same sort of thing that I did down here. And you could keep adding dimensions, if you wanted to. But anyways, yes. So those are array comprehensions. One thing to note about array comprehension is that, in creating an addition table in this third way, this was the first time that we didn't actually have to initialize an array of zeros first. So, when we created an array, there was an addition table here, for example, we started by using this fill command to get a matrix of zeros, and then later did this update, but we kind of did everything at once with an array comprehension. So that can be convenient. So that's it for notebook 4. And with that, we will go to notebook 5 on conditionals. Okay. So the keywords that we need to write a conditional statement in Julia are the if, else if, else and end keywords. And so my first example of doing a conditional statement in Julia is the FizzBuzz test. So for those of you that haven't heard of this, the FizzBuzz test is this thing that people will talk about on the internet. It's an interview question for people applying to be professional programmers, where the challenge or the interview question is, you're given a number or a set of numbers, and if the number is divisible by 3, you want to print fizz. If the number is divisible by 5, you want to print buzz, and if it's divisible by both 3 and 5, you want to print FizzBuzz. And so this is my implementation of FizzBuzz in Julia, and we need a number 42. That's always the best number. Okay, so n is 42. So here I'm checking to see if a number is divisible by 3. So note that to check equality in Julia, I'm just using a double equal sign. And then here's that modulo operator. And also to say and in Julia, I'm using this ampersand. And so this is our FizzBuzz implementation. And here we're printing fizz because 42 is not divisible by 5. It is divisible by 3. Yeah, so this is what a conditional statement looks like in Julia. Another way to write conditional statements in Julia is with ternary operators, which do exist in other languages, but I had never seen them, at least as a Python user, I'd never seen them until I came to Julia. So ternary operators are of this form. So A here is our condition, just like the A that we might have in a statement like this, if A, B, else, C, end. So here in a ternary operator, we're doing the same conditional evaluation, but now our condition comes before a question mark. After the question mark comes the statement about whatever we want to do if that condition is true. And then we have a colon, and then following the colon is a statement about what we want to do if our condition is false. And so, for example, say that we have two numbers, x and y, and we want to compare the value of x and y and then return the larger number. So in this case, 65 is slightly larger than 1, and so we are printing 65 because that's the larger number. And if we wanted to rewrite this code block with a ternary operator, it would look just like this. And if I execute that, we get the same output. So those are kind of fun and nicely clean. Another fun thing to talk about while we're talking about conditional evaluation is short circuit evaluation in Julia. And so just above we saw, I think this was the first time we've used it today, this and sign. We saw this and sign in Julia with the single ampersand. And so a statement like this is going to return true if both A and B are true. But the thing is that by default, Julia is going to eagerly evaluate an expression like this, which is to say that Julia will always look at B to see if B is true, or false, independent of whether or not Julia has already determined that this first condition is false. So if, for example, we were to say something like this, Julia would see immediately that this first condition is false, but Julia would still spend time looking at the second condition. And that's important, or rather that default behavior exists for something called bitwise operations, but it can be, unfortunately inefficient, particularly if the thing that you want to evaluate, or the second condition, if that is computationally expensive, then you might want to avoid evaluating this expression if you already know that that's not a worthwhile calculation for you to do, because this is already determined to be false. So if you want to short circuit this evaluation, you can do that by saying and with 2 ampersands rather than with 1 ampersand. So if I say A and B, I'm going to get short circuit evaluation, so I'm only going to bother evaluating B if I already know that A is true and that there's hope that A and B will both be true. So we can do that like this. Mark down. And examples of that. So here, we get to the point where we print x, which is 65, because x is larger. Here, we return false as soon as we evaluate this statement, and we never get to the point where we would print the number 1. Similarly, we can short circuit OR statements. So we haven't seen this yet, but the OR statement is done with these vertical lines. So I could say, true or false, and that's going to return true, false or true. Yeah. So in this case, we are going to get to the point where we print hi, even though we already have enough information to know that we could exit or stop evaluation after we've seen our first true. So if we wanted to avoid this and short circuit here, we can just use a double vertical line. And there we print true, and we never get to the point where we actually print hi. So that is it for conditionals. And now we go to notebook 6, which is, for some reason, my favorite notebook. It's on functions. I like the functions notebook. I hope the background noise isn't too bad. I'm in a co-working space right now. Okay. There we go. All right, so in this notebook, we get to talk about how to declare functions, duck typing in Julia, and then we will talk about something called mutating functions, mutating versus non-mutating functions, and if you don't know what I mean by that, that's totally fine, I will explain that. And then at the very end, we will talk about something called higher order functions. So, first off, how to declare functions. 3 different ways to do this. The first way is to use the function and the end keywords. Now, after the function keyword, we'll put the function name that we're creating, and inside parentheses after the function name, we're going to put whatever inputs that function might require. So here I'm creating a function called say hi that's going to greet its input, and here I'm creating a function called f that will square whatever input you give it. And I can call either of these just by passing it the inputs that it needs. So here I'm greeting C3PO, and here I'm squaring 42. Now alternatively, rather than using the function and the end keywords, I could have just written the function name and any inputs required inside parentheses after the function name, and then I could separate the function body from that name with an equal sign. So here I'm creating the function say hi version 2 and the function f version 2. And calling them is exactly the same. Now we're greeting our 2d2 and again squaring 42. And the third way that we could have declared a function is as an anonymous function or a lambda function. And so the reason that these are called anonymous functions is because you don't actually have to give them names at all. But if you don't give them a name, there's no way that you can access them after you've declared them, which sounds silly at first if you haven't ever seen anonymous functions before. It's like, why would you ever want a function that you can't call? It doesn't make any sense. But there are actually cases, as we'll see at the end of this notebook, where you can use a function even if you don't have a name for it. But for now, if you do want to declare a function this way, and also access it later, you can bind a variable to that function. And for example, now I have the variables sayHi3 and f3 bound to these functions. And the other thing to note is that the input arguments here are to the left of this arrow, where the arrow is a dash and then a right pointing arrowhead, and then the function body is after the arrow. So that's what the syntax for that means. And then luckily, calling functions that are created this way, if we've bound a variable to them, looks exactly the same as the other ways. Okay. So functions in Julia tend to just work on whatever inputs make sense, or for whatever inputs there exists a well-defined operation that will allow the function to execute or do what you're asking it to do. So I'll show you what I mean by that. So say hi, for example, thus far I've passed strings, and then say hi will throw those strings inside other strings to greet whatever the input was. And so Julia figures out that a sensible thing to do if I pass a number, for example, to say hi is to just interpolate the output string such that we greet the number now. Similarly, I've called the function f, which squares its inputs on just scalar numbers thus far. But if we were to have a matrix A, for example, if I call f on A, multiplication is a well-defined operation. I should say exponentiation and multiplication by way of, or exponentiation by way of multiplication, because again, when we call the exponentiation operator, that caret sign, we're calling multiplication under the hood. So multiplication is a well-defined operation for matrices, and other matrices. So if I call f on A, I'm just getting the square of matrix A. Similarly, if I write, string star string, I'm going to get string concatenation. And so if I call f on the string hi, this is a well-defined operation, so it works. I'm just, doing concatenation when I square the string hi. On the other hand, there is no well-defined way to, or no unambiguous way rather, to multiply a vector by another vector. If you're just asking for the product of two vectors, it's not clear if you want, for example, the inner product of those vectors or the outer product of those vectors. And so if I have a vector, here called v, which is just a 1D array, if I call f on v and try to square v, I'm going to get this error message that says I can't multiply two vectors. So that's an instance of where something doesn't just work. Because Julia can't make a guess about what we really mean in that case. So this third section is on mutating versus non-mutating functions. And so when I say mutating functions, I mean functions that will update or mutate the or some of the inputs that have been passed to that function. Whereas non-mutating functions do not update their inputs. So when you have a function, it has an input and an output. In either case, you're generating, you're doing whatever your function body wants you to do to generate, some output. But in the case of non-mutating functions, the inputs haven't been updated. That was kind of a confusing concept to me when I first heard about mutating functions, because I was like, wait, functions always do something, and if a function is non-mutating, it's still doing something. It's still creating an output. It's just that it didn't have to alter the inputs in order to generate that output. And I'll show you now what I mean by that, or give you an example of a mutating versus a non-mutating function. But first, the way that we tell the difference between whether a function is mutating or non-mutating in Julia is by whether or not that function terminates with an exclamation point. So just by convention, functions that are mutating end with exclamation points. So we already saw the functions pop bang and push bang, for example, which both ended with exclamation points because they were mutating functions in the sense that we would give them an array, and then we would add an entry or take away an entry from that array rather than creating a new array that had one more or one less or one fewer entry. And so, for example, sort which we'll see in a second, is non-mutating, sort bang is mutating. So for example, let's say that we start with a vector v, and this vector is unsorted, and if we call sort on v, we return the sorted vector, the sorted version of v. But if we look at v, we see that v is not updated by this call to sort. It's still 3, 5, and then 2. On the other hand, if we call sort bang on v, we're still getting this sorted output vector that is 2, 3, and 5. But if we look at v itself, v also is updated now. v is the sorted vector. Okay, so that's mutating versus non-mutating. And if you want to learn about higher order functions, that is our next section. So higher order functions are just functions that take other functions as their input arguments. A classic example of a higher order function is the map function. So the map function takes as its first input a function. As its second and any subsequent inputs, it takes collections. And so then what map does is that it takes the function that you've given it and it applies that function to every element of the collection or collections that you've passed, depending on what the inputs to f are. So in this case, f just takes one input, so map is going to run the function f over all the elements of just this one collection here, the vector that holds 1, 2, and 3. And so when we call map like this, we're getting an output vector that has the squares, or that's called f, on each of the elements of this input vector. And now, one of the things that's interesting about higher order functions is that this is one place where we can make use of anonymous functions that really don't have names, that we haven't bound a variable to, for example. So for example, here I'm passing this anonymous function that takes some input and then cubes whatever that input is. I'm passing that function as the first input to map, and now when we run this, we're getting the element-wise cubing of all the entries of this input vector. Okay, so another higher order function in Julia that's pretty cool is this function called broadcast. Now broadcast is really a generalization of map, so it can do some things that map is not capable of doing. But for the purpose of this tutorial, we're going to treat broadcast like it's basically a clone of map with just a different name. So we're only going to consider cases where broadcast does the same thing as map. So if I call broadcast on f and then this vector, I'm getting the same output as above. So what's cool about broadcast, if we're just going to treat it still like a clone of map with a different name, is that we can call broadcast without explicitly saying the name broadcast. So we can broadcast a function over a collection like this by instead calling the function and then putting a dot after the function name. So for example, if I say f dot vector 1, 2, 3, I'm getting that element-wise squaring of that vector. Similarly, to drive in the point, let's say that we have now a 2D array, A, that goes from 1 to 9, the upper left to the bottom right corner. If I call just the function f on A, I'm going to get A squared, or A times A. On the other hand, if I call f dot A, I'm going to get element-wise squaring of the matrix A. And so what's cool about the fact that we have this dot notation for broadcast in Julia is that it allows us to write maybe more complicated mathematical expressions in a way that looks more natural or closer to the math than we might write down on paper. So for example, this expression and this expression do the same thing, but it's easier, I think, to look at this first version and have a sense of what's going on, just to know that, okay, all of these operations are element-wise. Whereas in this case, we're making this explicit call to broadcast, we're declaring a lambda function, and then we're passing A as the collection that we're going to update. And so that's it for higher order functions. And with that, we can move on to notebook 7, and just as sort of like a roadmap. So these first, I guess, 6 or 7 notebooks, depending on whether you count the Jupyter Notebook one, is all about, or are all about, like getting you sort of an intro to just language syntax. Looks like I should probably log out and log back in. So I'll do that while I keep talking. So yeah, the first up to notebook 6, the idea is to just do an overview of the language to give you a sense of, what working in Julia looks like. And now that we're done with those first few notebooks, we are going to do a few other things. The next notebook is on how do you use a package in Julia, so how do you take advantage of the larger Julia ecosystem. Then we'll look at some intro plotting in Notebook 8. Notebook 9 is the one where we get to do benchmarking, so we'll see how fast Julia is. And then after Notebook 9, we're going to talk about multiple dispatch, which is the design paradigm for Julia. So we'll talk about why is Julia fast? Why is Julia performing so well? And at the very end, for those of you that are still interested, I'll have a couple notebooks on linear algebra. So notebooks 11 and 12 are both on linear algebra. 11 is just like a cursory, okay, how do we solve a linear system? How do we multiply matrix by vector? How do we take transpose? That sort of thing. And then notebook 12 then, the final notebook is called Factorizations and Other Fun. And in that one, we'll see some more cool linear algebra things, including some performance tricks, like taking advantage of special matrix structure, for example. Okay, so these are the notebooks I just discussed: packages, plotting, Julia's fast, that's the benchmarking one, multiple dispatch, and then these linear algebra ones. So that's what we have left. And with that, I will go to Notebook 7. So we have about 1,700 registered packages thus far in the Julia ecosystem. So this is a growing number, and probably will grow much more after we've released 1.0 and the language is fully stable. If you want to see what packages we have to offer, you can go to pkg.julialang.org or juliaobserver.com. One of the things to note about the package system is that we offer first-class function calls to other languages. So, if you have some code that you already wrote in Python, for example, or R, and you want to continue to work with that code base that you've already created, or somebody else's code, some library, for example, in Python or R, so you want to keep working with NumPy, but you want to try out Julia, you can do that. You can start working in Julia while still relying on this other code that you or someone else has written by making use of the package system in Julia, so that you can, if you want to, kind of get your toes wet before jumping in and committing to transferring your workflows to a new language or what have you. Okay, so how do we use a package in Julia? So first off, you don't have to do this today because we're on JuliaBox. But if it's the first time that you are using a package on a new Julia installation, you would want to run this pkg.add command. And so pkg here, this is our package manager. So here you're just asking the package manager to install or add this package. And the package in question here is the example package. So inside pkg.add, you're throwing quotation marks around the name of whatever package you want to add. Once you've done that once, you never need to do it again, and today you don't need to do it at all because we've already done this on JuliaBox for you. But every time you use a package, you need to load that package into your new notebook that you just opened, or into like a REPL session. So to load a package, you would use this using command. So here I'm saying using example, and so that means that I have access now to the function that is declared inside this example.jl package. And all the source code, very prolific source code for this example package, is at the link provided. And you'll see there that there's this function called hello, which greets its input, which must be a string. And so since we've used the example package, we can now call that hello function to print some lyrics. Okay. Another fun package to demo is the colors package. So again, we don't have to run pkg.add colors today, but we do have to say using colors. And now this gives us access to this function called distinguishable colors. And so here I pass the number 100. So we're going to get a palette of 100 different colors. And now that we've done that, one fun example is to use a palette with the rand command. So we've been using the rand command like this to generate, for example, a 3x3 array that has numbers between 0 and 1. I mentioned earlier that there were ways that we could randomly populate an array from other collections rather than just all the possible floating points between 0 and 1. And for example, if I wanted a random array, so I guess what I should say is that the first input argument to rand optionally can be a collection from which you want to populate the subsequent array. And so if I run this, then I'm going to populate this 3D array with numbers between 1 and 10, or integers between 1 and 10 rather. And if we want to populate with palette now, we can do that, and now we get this fun randomly colored matrix, which has a lot of green in it. Okay, so this one is fun because I get like a different color every time. That always amuses me. It never gets old. Alright, so that's packages. That's how you use packages. And please explore the package ecosystem and see what we have to offer at the provided links. And with that, we will move to Notebook 8. So that's on plotting. Okay, so to plot, oops, I didn't mean to restart that, but it's okay. And, overactive fingers there. Okay, I'm just gonna run this notebook. We can go through it relatively quickly. Okay, so today, well, I guess there are a bunch of different ways to plot in Julia. For example, like you could just use PyPlot if you wanted to from within Julia. We have wrappers around lots of existing plotting infrastructure out there. The package I'm going to use today is the package called plots, so plots.jl. And what I like about plots is that it allows you to change easily between different backends. So for example, you can use the plots package and you can say like, oh, I want to use PyPlot, but from within plots, or I want to use Unicode plots, or I want to use Plotly.js, or just Plotly, or GR. There are lots of different backends supported. But the idea is that the plots backend gives you a common set of syntax to create plots with, so that you can write code to generate a plot. You can change the backend later, and you don't have to recode anything. The syntax for creating your plot will still be the same. So we are going to use plots to plot some fun data that I data thieved from the internet. And so this data has, for a few years between 1860 and 2000, global temperatures, and also the number of pirates in the world. And so I guess I didn't data thieve what the actual years were. I don't remember if that data was provided or not. Yeah, as we read this array, for example, from left to right, these are the global temperatures as time increases for a few years between 1860 and 2000. And similarly, as we move forward in time, these are the pirate populations. So we can just see by looking at these arrays that global temperatures are going up, pirate populations are going down. Okay, so we're going to use the GR backend, which I call here, to plot this data. And so I've called GR there. Now I'm going to use the plot command to get num pirates and global temperatures plotted against one another. And here I'm using the scatter bang command. The reason that this is scatter bang rather than scatter, or rather the reason that I'm using a mutating function rather than a non-mutating function here, is that I'm using scatter bang here to overlay points with this existing or already plotted line. So if I instead call just plot and then scatter without this exclamation point, I'll get two different plots. So to create an overlay, I'm using a mutating function there. This is kind of weird. It's a little buggy. I got these like double outputs, which is odd. But anyways, now if we want to annotate our plot a bit more, we can use these xlabelbang, ylabelbang, and titlebang commands. Make this a little smaller so we can see everything at once. I feel like it's taking two jumps. Okay, there we go. Okay, so now we can see pirate populations going up as temperature goes down, and so this is a little wonky because it's kind of like we're looking backwards in time now from left to right, and the reason is that Julia by default plotted the data that we passed to it in increasing order on the independent axis, or the horizontal axis here. And so if we want to see what this looks like, what this data looks like going forward in time, we actually kind of want to flip the axis around. So I used here this xflipbang command. And then we can see more clearly that as pirate populations have decreased since 1860, we've seen this increase in global temperatures, which is quite concerning, and clearly we need more pirates. Okay, so now we can switch backends and use the Plotly.js backend, and otherwise use all the same code that we used before to generate the last plot. But now we have a slightly more interactive plot from Plotly.js where we can drag our cursor over the data and actually see what the values at that data point, at those data points are. And maybe the last thing I'll do here quickly, I'm just going to show how to do subplots. Oops. Okay, so the idea here is that to generate a subplot, we need to create whatever plots we want to sort of embed in that subplot and then name them. Having done that, we can take the names of those plots and throw them all into a new call to plot, and then we can specify the layout of those plots with this layout keyword. So here I'm just using a 2x2 grid. You can specify more, exotic layouts if you want. For example, you could do like, 2 on top and like one plot on the bottom, and you could, move the one on the bottom around to, kind of jiggle with the spacing and whatnot. To do all of that, you might want to look, in case you're curious, there's another plotting notebook that I'm not going to cover today. If you were to go to tutorials, it's tutorials intro to Julia for data science, and I think it's notebook 3 or 03 or whatever on like something plotting. In that notebook you can see how to specify more I guess exotic layouts, and also how to create like violin plots and box plots and histograms and all that sort of stuff. But yeah, so this was our basic introduction to plotting, and now we will go to notebook 9, which is our benchmarking notebook. Okay, so I'm going to run all. Okay, so this is a notebook that I talked about at the beginning of the tutorial. So this notebook is where we are going to look at different implementations of the sum function. So in the beginning, or in the intro, I mentioned that we were going to look at handwritten versions of the sum function in C, Python, and Julia. We're also going to look at built-in versions of sum in Python, NumPy, and Julia. And so for all of these different implementations, we're going to be benchmarking using this vector called A, which will take 10 million elements, or it has 10 million elements rather. And we do a couple sanity checks throughout the notebook. So for example, if we call sum on A, we're getting about 5 million because we have 10 million elements times about 0.5 for each of the entries, since we use the ran command to populate this array. And so sum seems to be working. The built-in sum from Julia seems to be working the way we think it might. And then to do benchmarking in Julia, we are going to use the benchmark tools command. If you wanted to like time any function in Julia, you could use the @time macro. So for example, something like that. You could use the @time macro. But the thing is, the benchmark tools macro is going to allow us to get more like better statistical representation of how long it takes to run a given piece of code. So benchmark tools, when you time, is going to run a piece of code multiple times and then report like an average of how long it took to run and then what the minimum and the maximum runtime will work. It's still not perfect, so there's still going to be noise between one call to benchmark tools and another, or to a function from within benchmark tools rather. But it'll at least be better than using the @time macro. Another thing to note, actually that wasn't a very good example, because I want to play with something quickly and see if I can actually. Oh, because it already, what if I, so what I was trying to show, but yeah, sometimes what you'll see is that when you run a piece of code once, the first time it'll be slower and have like more allocations than the second time that you run it. And I don't know if this is just a bad example or if like it already knows what I want to do. But the reason that there's that performance difference between the first time you run a piece of code and the second time is that the first time you're actually doing compilation, and the second time that if you rerun something you've already compiled, then you are using the compilation from the first run through, so it will be faster. Okay, so that aside, we can now move into looking at our actual implementations of sum. So the first is the handwritten version in C, and I didn't write this notebook in particular, so I did not write any of this in C. But the important thing to note is that we're creating a function in C here. We are compiling that from within our Julia environment, and then at the end we have this function called csum, which when we call it is going to call to C under the hood. And so we have some sanity checks on csum here, where we see that when we use csum, we get about 5 million for all the elements of vector A, and then we can be a little bit more precise than that and check that csum's output is approximately the same as sum's output. And we do that with this curly equal sign, which calls the isApprox function under the hood, where isApprox checks to see that two things are equal within some tolerance, so you don't have to worry about like floating point error if you're asking if two things are the same. And so, having done those sanity checks, we can then use this @benchmark command to benchmark A inside csum. And so what we're seeing here is that the minimum time that it took to add together these 10 million elements was 11.665 milliseconds. And so then what we're going to do is we're going to grab that minimum value from our benchmarking and add it to this output dictionary called D that we'll use to keep track of how well each of these different implementations of sum did. Now second, we'll look at Python's built-in sum. And so to grab built-in functions from Python, we can use this pycall package. Here, this is allowing us to work between Julia arrays and a Python data structure. Here we're using this pybuilt-in command from the pycall package to grab the sum function and then rename it here as pysum in our environment. And then we call pysum to do a couple sanity checks, and we benchmark pysum here. Having benchmarked pysum, we see that the built-in version of sum from Python is taking a little over 155 milliseconds. And if we add that best time to the output dictionary D, then we can move on to our next built-in version of sum. So the next built-in that we're going to look at is the built-in from NumPy. And to grab NumPy functions, here I'm using the conda package. And then we're using pyimport, for example, to grab that function from NumPy. And we do our benchmarking here. And now we see that it took 6.7 milliseconds to add together all the elements of vector A using NumPy. And when we add that best case scenario to our output dictionary, one of the things to note is that Python's NumPy is doing better than C. And the reason for that is that NumPy is calling C code under the hood, but that code is going to be more optimized than the sort of brute force looping thing that we did in C in the handwritten implementation in C. So far Python NumPy is doing the best. Then we can move to the Python handwritten. So here is that handwritten code inside our Jupyter notebook, and we're designating that this is Python code with this py next to our basically our string created with 3 double quotation marks. And then we're calling this sumpy now rather than pysum, and we're going to benchmark this function sumpy. And what we see is that the minimum runtime is about 461 milliseconds. We do some sanity checks, and we add that best case scenario for the Python handwritten to our output dictionary. Okay, so now that we've looked at C and Python, we can look at Julia. So let's start by looking at this sum function that we started with in the notebook. So if we benchmark this sum function, we see that here it took about 6.5 milliseconds to add together all the 10 million elements of vector A. And if we add that minimum to this output dictionary, we can move to our last item, and then we'll do a comparison of everything against everything else. So the handwritten of my sum in Julia looks like this, so very similar to that Python code that we saw above. And then if we benchmark my sum, we see that the best runtime is about 12.5 milliseconds. with our handwritten Julia. So we add that to our output dictionary. Now we can order all of those entries and print them nicely so they're readable. And so what we're seeing here is that Julia's built-in did the best in this case. And as I mentioned before, just to be like fully upfront, as I mentioned before, from one runtime to another using benchmark tools, we get some noise. So sometimes when I run this notebook, Python's NumPy does better, and sometimes Julia's built-in does better. So it's noisy there as to whether Julia's built-in or Python's NumPy is doing better. But the thing to note here is that, in case you didn't read this above, Julia's built-in is written in Julia itself. So we're getting this speed relying on Julia, not by, like calling C code under the hood. And then we can look at our handwritten versions, and we can see that here C is doing better than Julia's handwritten. But Julia's handwritten is most of the way there. And another cool thing is that when we move from Julia's built-in to Julia's handwritten, there's less than a factor of 2 performance difference there. And not only is it less than a factor of 2 performance difference between the built-in and the handwritten in Julia, but that factor of 2 is only amounting to a handful of milliseconds. So you're getting most of the way there with performance in Julia when you're just doing this kind of simple thing that we didn't think about so much. Whereas if you were to compare like Python's NumPy with Python's built-in, or even just Python's built-in with Python's handwritten, you're losing here between Python built-in and Python handwritten code. You're losing a factor of 3 performance, and that performance difference is amounting to hundreds of milliseconds rather than just a few. So I think this is a really good illustration of how easy it can be in Julia to write really performant code. And with that, we will ask the question, why is Julia fast? Where the answer is, or at least part of the answer is, Julia's design paradigm, which is multiple dispatch. And so we'll talk about what multiple dispatch is here, and then we'll quickly go over some linear algebra stuff before I let you guys go. Let's check. Okay. Let's see how long I have this room for. All right. So to talk about multiple dispatch, I'm going to start by talking about things that we've already seen. So we've already seen that we can declare a function without thinking at all about the input types to that function. And then Julia will figure out that this function that squares things f, it's going to work on numbers, it can work on matrices, it can work on strings, but it can't work on vectors because that's not a well-defined operation. And so what does this mean? So what this means, or maybe where we can go next from this, is that we haven't specifically given Julia any information about what the input types to f can be when we declared f here. But if we want to, we can provide additional information. So let's talk about that next. So if you want to tell Julia explicitly about the types that you want a function to accept, you can do that by annotating your input arguments to a function. And you do this annotation with with 2 colons or a double set of colons. And then the type, or the name of the type that you want that input argument to be. So here we're declaring a function called foo. This function called foo will take 2 inputs, x and y. X and y are each going to be a string. And then when we pass 2 strings to foo, we want this output, or this print line statement to be called, which will print out a statement saying x and y are both strings. And so we've declared foo in this way. So if we call foo on the strings hello and hi, we're getting this expected output. If we call foo on 3 and 4, we're just going to get an error message. And the reason is that there isn't a version of foo. Foo does not take 2 integers. It doesn't take numbers. So if we want foo to work on integer inputs, we could annotate x and y accordingly. So here we're saying x is an integer, y is an integer, and now when foo is called, we want the output to say inputs x and y are both integers. So now if we call foo on 3 and 4, we're getting that expected printout. But the thing is, if we go now to call foo on hello and hi, we're still getting the output that we got above when we called foo on hello and hi. So the idea is that when we declared foo in this second way, when we said that foo can take x and y as integers, we were not overwriting our initial definition of foo, which takes strings. We're not overwriting it, we're not replacing it. What we're doing is we're adding another method, or we're adding a second definition to an existing function in this case. And so this starts to get into the heart of multiple dispatch, where in multiple dispatch we have this, we make use of a distinction between generic functions and methods. So generic functions are sort of the abstract ideas that are tied to particular operations. So like in our minds we have an idea of what it means to add two things together, and we often associate addition with the plus operator. And for us, like, there's no distinction between adding together 3.0 and 3 versus like 3.0 and 3.0. But on a computer, if you want to actually add things together, you need to pay attention to what the concrete types of those things are. And so, for example, you need like specific ways to, for example, add together 3.0 and 3.0 versus like 3.0 and just 3, because it matters if you're adding together an integer and an integer, or an integer and a float, or a float and another float. And so these specific implementations that actually deal with particular argument types are methods. And in Julia, we as users can, if we want to, just think about generic functions. We can just think about sort of these abstract concepts like addition or multiplication. We don't have to worry about types. But there exist for most functions, there exist many different methods that will work on a bunch of different types. And so the idea is that we don't have to think about the types, but the compiler still gets the additional information from being able to know what specific types are. So the compiler is able to use type inference. When you call a function, the compiler looks at all the inputs that you've given to that function and then determines like which method should I send off, which method should I send that's going to generate really efficient machine code for the particular operation that you want done. So the compiler picks that method, dispatches it, and it does that without you ever having to think about how would I get like efficient code for this type of input. And so I'm going to show you a couple commands that'll kind of give you hopefully a sense of what's going on here. So if we call methods, for example, this methods function, if we call methods on foo, we can see what methods exist for this generic function foo. So we can see that those two definitions that we wrote, one for in64s and one for strings, are both available to us. We can furthermore see that if we call methods on the plus operator, for example, if we call methods on plus, we see that there are 180 different ways to add things together in Julia. So this is basically a combinatorics problem where, how do we add big floats to big ints, and like how do we add here dates to days, for example. And so there are all these different ways to add things together. Now, if you want to know which method is being deployed when you make a specific function call, you can use this @which command. So if I say @which on foo 3 and 4, it's going to tell me which method or which version of foo is being dispatched when I pass the inputs 3 and 4 to foo. And so the answer is it's this version of foo that takes 2 integers. Similarly, if you were to call like @which on 3.0 plus 3.0, the version of addition that's being used here is the version that's specifically written for float 64s. Another thing to consider when we're talking about multiple dispatch and like which methods are being dispatched is this notion of like concrete versus abstract types that I mentioned earlier. So we have this abstract type called number, for example, where number includes like all integers, all floating point numbers, for example. So when you pass a given set of inputs to a function in Julia, the method that's going to get used, or the method that's going to get dispatched, is the one that that is associated with like the tightest constraints that can be placed on, or how would I word this? I'm just going to give a specific example rather than trying to make an abstract statement. So for example, we have right now, if I declare this, now we have a version of foo that takes 2 numbers, 2 abstract type numbers. We also have this method for foo that we wrote above that takes 2 integers. Now, if I were to pass, for example, 2 floating point numbers to foo, what's going to happen now is that we're going to get this numbers version being used, which we could figure out using the @which command or just by looking at the input based on how we've written foo. So here the numbers version of foo is being called. Even though we have this numbers version, if we call foo on 3 and 4 at this point, we're still using the integer version for 3 and 4 because integers are a more specific type, say, than this abstract number type. And then we can always create fallbacks, like fallback duck type methods, for example, where we didn't specify exact types. So for example, if we were to just declare foo without adding any type annotations, now we have a version of foo that will take whatever we want to pass it. And in this case, if we call foo on a vector v, for example, we're going to get this generic fallback version. So that is our intro to multiple dispatch. And with that, I will move on to the linear algebra section. So we'll leave there. Okay, basic linear algebra. Okay, so this is the notebook where we see how to multiply, transpose things, and that sort of thing. So we'll start by defining a linear system. So here I have a matrix A, a vector x, and then we can multiply A and x together using just the star operator as we've used before to get matrix vector multiplication. If we want to transpose a matrix, we can get conjugate transposition with an apostrophe after the name of a matrix. Or if we want just transposition without getting the conjugates, we can use the transpose command. Julia does allow us to write transpose multiplication without a star operator, so we don't explicitly have to say A prime star A. We were able to just write A prime A, and Julia was able to figure out that we wanted to multiply these objects together. And then, if we want to solve a linear system, as with other higher level languages, you can just use a backslash. So here A backslash B is going to give us the solution X to this linear system, except it won't work if I have randomly initialized a singular matrix. So I'm going to there we go. Okay, so hopefully we don't get a singular matrix again. Alright, okay, so now we've gotten our solution to this linear system, which is the same vector of 1s we created up here. Using a backslash to solve a linear system will work on matrices of different types and sizes, for example. So say that we have a tall matrix that has more rows than columns, so one that's overdetermined. If we call A tall backslash B, we're going to get now the least squares solution to this overdetermined system. If we had, here I'm creating a rank deficient problem, so I'm doing that by using the same vector as the columns of the matrix rank def that I'm creating here. And then we get the minimum norm least squares solution now if we call a backslash. And in this last example, we have an underdetermined system, and again, we're getting the minimum norm solution when we call A backslash. So we're here, dispatching the method appropriate for whatever matrix we've passed here when we call this sort of general backslash function. So that's our intro to linear algebra. And with that, we will move to our very last notebook of the day, which is notebook 12, Factorizations and Other Fun. And okay, so in this notebook, we're going to start by talking about factorizations and what the syntax for those looks like in Julia. And then we'll talk about special matrix structures and then quickly mention generic linear algebra support in Julia. So we start here by creating this linear system. And then the syntax for doing factorizations in Julia is pretty similar between doing different types of factorization. So for example, if you wanted to perform an LU factorization in Julia, you would use the LU fact command. And we'll see below that we also have SVD fact and HES fact and QR fact. And when you call a command like LU fact that performs a factorization, the object that you will return is a factorization object. So the type of this output ALU here is this LU array. And what this LU array contains is a few different things. We have the permutation matrix that we would get from this LU factorization, that matrix P. we would also get the lower triangular matrix L and the upper triangular matrix U. So if we want to grab any of those individual objects from our factorization object that stores all of them, we would index into the factorization object using the symbol that corresponds to whatever particular matrix we want to grab is. And so the symbol P for an LU factorization refers to the permutation matrix that comes out of that factorization. The symbol L will give us the lower triangular matrix, and then the symbol U is going to give us that upper triangular matrix from this factorization. And so those symbols that we need to index into the matrix are going to change based on the type of factorization you're doing, but you can just always look at the documentation in order to figure out what symbols you need. And when I say symbols, for those of you that aren't familiar, a symbol in Julia is a colon preceding some name. So colon U is the symbol U, whereas if I did that, that would be like the variable U, which is as of yet undeclared. It's also worth noting that once we have a factorization object, we can dispatch on the factorization object in order to solve a linear system. So for example, we could call A\B to solve the linear system, AX equals B, or we can solve that same linear system by dispatching on the factorization object and get the same result. Similarly, we have methods for factorization objects for like the determinant function, for example. So you could use the factorization object to get the determinant of A just as easily as you could from the matrix A itself. QRFact will allow us to do a QR factorization. As with LUFact, we can index into this object with the Q symbol and the R symbol. So that's pretty similar. Eigendecompositions are done with EigFact. The symbols that are relevant to an eigendecomposition are colon values and then vectors here. So those will respectively give us the eigenvalues and the eigenvectors of the input matrix. And note that if we were to take the inverse of the factorization object that we get from an eigendecomposition, what we're really doing under the hood is we're making use of those eigenvectors and eigenvalues in order to calculate the inverse. Okay, so this next section is on special matrix structures. Now to give you a sense of, I guess, what I mean by special matrix structures first. So when I say special matrix structures, what I mean is that when you have a matrix, often that matrix will have data organized in a patterned way. So for example, you might find that you're working with a symmetric matrix where, on one side of the diagonal, all of the entries are going to be like the same of their mirror entries on the other side of the diagonal. Or you might have like a diagonal matrix, for example, a matrix that only stores non-zero entries on the diagonal itself, and everything else is going to be non-zero. Now Julia has ways both to recognize and to explicitly report when a matrix has a structure or an underlying pattern like this. And the reason that that's important is that it allows you to do optimizations both with the types of operations you're doing and also with the way that you store things in memory that will allow you to write much more performant code and code that's capable of doing things that you couldn't otherwise do. So for example, you can imagine if you're working with really large matrices, this becomes very important. So for example, if you have a million by million matrix, so a matrix that has a million columns and a million rows, if it's diagonal, that means that you only have a million values that are actually not zero. So only 1 in a million of your entries in that matrix will be non-zero. And so you can imagine that if you can tell the compiler, or if the compiler can figure out on its own that I can ignore 999,999 of these entries and just note that they're zero without explicitly storing them, you're not only saving room in memory, but you're saving yourself time every time you otherwise would have had to multiply a zero by another zero. And so taking advantage of special matrix structure is important, and we can show that by starting with this randomly initialized matrix that's 1,000 by 1,000, and then here we're symmetrizing the matrix and asking Julia if the matrix is symmetric. Julia is able to recognize that it is, and so that's great. But the thing is that when you're working with linear systems on a machine, over the course of doing matrix-matrix operations, matrix vector multiplies, your objects are going to accumulate some error. And that error can get in the way of the compiler's native ability to recognize the underlying structures. So for example, we can model that by making a copy of this matrix called asym that we'll now call asym noisy. And then we're going to index into just one entry out of the 1000 by 1000 matrix. And we're going to add a little bit of noise. And to give you a scale, I'm actually gonna, oops, just to show you. Okay, so the noise that we've added is order of 1 to the negative 50, or sorry, yeah, 10 to the negative 15. And the compiler cannot make assumptions that this isn't intentionally added. The compiler can't just assume that that's noise. And so the compiler, if we now ask Julia, like, is asym noisy symmetric, Julia has to respond no or false. So if we want to take advantage of the special matrix structure that we know is there, and ignore the noise that the compiler can't interpret as, you know, noise versus intentional signal, say, we can use these functions that will explicitly declare our matrix structure. So, for example, we can explicitly say that asym noisy is a symmetric matrix, and I'm doing that here by creating this matrix called asym explicit. And then we can time how long the same operation takes based on, you know, whether we're using the original matrix, asym, that the compiler recognized as symmetric, versus this noisy version, versus the version of the matrix that has been explicitly told is a symmetric matrix. And so what we see is that, and here we're just using the @time macro, you know, it's order of 2 seconds if we calculate the eigenvalues of the matrix that Julia recognized was symmetric. It takes order of 20 seconds, so, you know, more than an order of magnitude longer when we work with this noisy one. And then here, when we're working with the symmetric matrix, getting a lot of noise in my @time macro. It's, yeah, order of 2 seconds here. To be more precise, we want to use benchmark tools, because as you probably saw, I got 4 seconds on one of these runs. So wide variance. But the idea is that, you know, though there may be variance between this call, for example, and this call based on, you know, the @time macro and whatever else is going on in the background, or however I'm passing information over the internet, certainly the difference between performing this operation on the noisy matrix and, you know, either of these is significant with that more than order of magnitude difference, or order of magnitude difference. And the last thing I wanted to show with regard to special matrix structure is here I'm creating, I'm declaring the number 1,000,000, and then we're creating this matrix that's symmetric tridiagonal, so, you know, only, depending on how you're counting, 2 or 3 diagonals that have non-zero values. You really only need to store 2, because 2 of them are going to be the same. So only 3 of those are non-zero. And so if we want to grab we want to calculate the maximum eigenvalue of this matrix A, we see that it takes a little over a second because we've told Julia explicitly that this is a symmetric tridiagonal matrix. Whereas, you know, if we had just stored this as a dense matrix, if we had actually accounted for all of the, you know, millions of zeros in that matrix, then we wouldn't even have been able to solve this problem on the laptop that I'm using. And the very last thing from the tutorial today is about support for generic linear algebra. Just make sure it doesn't appear anyone's waiting for this room yet. So, okay, so one example of, you know, generic or support for generic linear algebra in Julia is that Julia has, you know, built-in rational numbers, and that you can create linear systems, for example, that are, you know, based on rational numbers, and Julia will continue to work with rational numbers in those objects as you perform whatever operations you're interested in, rather than, you know, dividing out the numerator by the denominator in a rational number and getting, you know, a decimal point or a floating point number. So I'll show you what I mean here. So first off, to create a rational number in Julia, you use a double slash. So this is the rational number 1/2 rather than the floating point 0.5. And here we're creating a matrix that stores all rational numbers. So what we're seeing here is that if we multiply this matrix A rational times x, our output vector also has rational numbers. Similarly, we can solve this linear system now and get a vector that has rational numbers. We can even, we can do an LU factorization, for example, and the output vector, or the output object is going to store objects with all rational numbers. So that is an example of offering support for generic linear algebra in Julia, and that is the last notebook of the tutorial. So if you scroll all the way down, this is that feedback link that I gave at the beginning of the tutorial. It's also currently in the YouTube description, and I'll leave that up for a little bit. And otherwise, that is all. Okay, so there's the link there. Otherwise, maybe I'll just go to my slides to remind you about our other resources for learning Julia things or talking to the Julia community. So links on Slack, Discourse, GitHub, again, my email. And with that, we are done. So thank you so much for tuning in. Thank you to Simon and Chris for showing up to answer questions. And I'm doing another one of these on, I think, May 4th, but in the meantime, we have our tutorial in Spanish tomorrow, and then later in May we'll have some other tutorials on packages, data frames, and dynamical systems. So thank you so much for tuning in, and that's all. Have a great weekend. Bye.